All right, so we're going to look at the cross product, lecture 27 of specialist maths. Some of the prior knowledge for this will be introduction to vectors, resolving vectors into rectangular components. As well, dot product's not super important, but it's going to be important to know the difference between the cross product and the dot product. And the dot product's a bit easier, so it's probably good to have some practice with that. And some basic trigonometry will be very helpful for this as well. So some of the key concepts we're going to cover are the geometric definition of the cross product. So we'll look at the magnitude of it, the direction of it, the properties of it, and then we'll look at the cross product between parallel and perpendicular vectors. We'll also look at the cross product of component vectors, the component definition of the cross product, and then how we can compute the cross product. So it's a fair bit to get through, but it's a very interesting idea. So let's jump into it. First thing we're going to look at is the geometric definition of the cross product. Sometimes it's known as the vector product. So if you see vector product written anywhere, just be aware that it's the same thing. So let's think about what is the cross product. So the cross product of two vectors A and B is denoted as A multiplication sign or across B. And the magnitude of A cross B, so how long? So firstly, the cross product is a vector. So it's a sort of an operation you apply to two vectors and you get a vector as your result. And then so what we're talking about is the magnitude of that vector. And the magnitude of that vector is the magnitude of vector A multiplied by the magnitude of vector B multiplied by sine of the angle between them. So yeah, theta is the angle between vectors A and B. Okay, the direction of A cross B is perpendicular to the plane containing A and B in the sense of the right-hand rule. We'll talk about that in a moment. Let's just look over here at this diagram for our vector cross product. If we've got some vector A that's just some arbitrary vector in space that's pointing here, and they've got some other vector B, just ignore everything else that's going on for now. What we can say is, if you were to think about the plane that contains A and B, if we get the angle just right, I think you would agree that that sort of plane is in that direction there. So that sort of blue surface is the plane that contains A and B. And then you'll notice we've got this sort of vector pointing out of the page. You'll notice that that vector that's pointing out of the page, this one here, is perpendicular to A and B, and that is in fact the cross product, that is the resultant vector. So it's sort of pointing out of the page. Now, the question is, how big is this vector? How do we know to make it this size? Basically, in simple terms, two vectors in space, A and B, will always create a parallelogram. Okay, so you can see that that's the shape we've actually got here. If we take vector A and then add A to the end of B and then add B to the end of A, we'll get a parallelogram. The area of that parallelogram is the length of the cross product between A and B. And that is what the cross product is, okay? Now you're probably thinking to yourself, there's two ways that a vector can be perpendicular to that. It could be going sort of into the page, but we can see here it's sort of coming out of the page. But that's because we're crossing A with B and not B with A. So we'll talk about the right-hand rule in a moment in the direction, but it's coming out of the page because we're going from A to B. In any case, let's just stick with the idea of the magnitude for now. So by definition, we have that the magnitude of A cross B is equal to the magnitude of A multiplied by the magnitude of B multiplied by sine of theta, where theta is the angle between A and B. So from the diagram, the magnitude of A cross B is the area of the parallelogram spanned by the vectors A and B. So I think you would agree, if we just sort of draw that parallelogram in two dimensions, we'll get vector A and vector B. I think you would agree, just from some SOHCAHTOA, that this length here would be sine of this angle in here. So what we get is, if we multiply A by magnitude of A multiplied by the magnitude of B multiplied by sine theta, that gives you the area of that parallelogram, which is the magnitude of the cross product. Okay, so that is how we calculate that. Let's look at the next thing, which is the direction of the cross product. Okay, so you can see here we've got the same diagram going on, except this time we've got two vectors. We've got A cross B and B cross A. You'll notice B cross A is kind of into the page, right? So what we're going to do is we're going to think about what's going on. So we're going to use what's called the right-hand rule for the cross product. product. So to determine the direction of A cross B, use the right-hand curl rule. So point your fingers in the direction of A. So you can do this on the screen. So you point your fingers in the direction of A, and then curl your fingers towards B. So when we're doing A cross B, we're going like this, and then so we can see it's out of the page. And then when we do B cross A, we're sort of going the other direction. We're going from B, point our fingers in the direction of B, and then curl towards A, sort of going into the page. So that's why B cross A goes in the opposite direction. Okay, so your thumb points in the direction of A cross B, which is perpendicular to both vectors. Okay, I think you would agree that the cross product, as you can see, is not commutative. A cross B and B cross A give you different vectors. So it's not like multiplication, it's a completely different operation, and it's not commutative. You can't change the order without changing the meaning. Okay? Instead, we have a situation like this, where if we do A cross B, I think you'd agree that A cross B is the negative of B cross A. They're opposite, pointing in opposite directions. Okay, and just another property of the cross product, it's not associative. Okay, so associativity, 2 times 3 multiplied by 4 in number land is the same as 2 multiplied by 3 times 4. But in the cross product land, A crossed with B crossed with C is not equal to A crossed with B crossed with C. So that's something to be aware of. Okay, so that is sort of how we work out our directions of the cross product. Let's look at when we start to take the cross product of parallel vectors. So if we have two vectors A and B and they're parallel, then the cross product is equal to 0. So what you'll notice here is we've got a bit of a diagram. At the moment, if two vectors are parallel, then the angle between them is 0 by definition, right? So you can sort of see here, just for explanatory purposes, if I change the angle, you can see that another vector appears. We've got this vector here, A, let's call it, and this vector here, B. If they're parallel, then the angle between them is 0. And so we get sine of 0 when we compute the magnitude. And so that's equal to 0. So we can say that the magnitude is 0. Conversely, blah, blah, blah. Yeah, if A cross B is equal to 0 and both are non-zero, A and B are parallel. Okay, so yeah, basically if the vectors are parallel, you get the 0 vector as the cross product between them. Okay, so let's think about when they're not parallel. So the cross product of perpendicular vectors, you'll notice as we sort of open this second vector, the cross product is represented by that other vector there. So let's put this to 90 degrees and sort of explain what's going on. You'll notice that these vectors here, vector A and vector B, have magnitudes of 2, just by sort of looking at it, right? Okay, so that's going to form a parallelogram. In this case, that parallelogram will be a square. Okay, the area of that square will be 2 times 2, which is 4. And we know that the direction will be perpendicular to the plane containing A and B. So again, using the right-hand rule, point your fingers in the direction of A, curl towards B, and then the cross product direction vector will be pointing up, and you'll notice it has a magnitude of 4. So that's sort of what's going on there. And just interestingly, if we just change these values, obviously the cross product, as the angle between them gets closer together between A and B, the cross product gets smaller and smaller. I encourage you to think what will happen to the cross product when the angle is 180. I think you would agree that the cross product would go to 0 because they are parallel. When they're 180 degrees separated, then they're parallel, so the magnitude of the cross product is 0. Okay, so I think that's pretty interesting. Okay, so if A and B are perpendicular, so that means A and B are at 90 degrees apart, so let's make that 90. If A and B are perpendicular, then the magnitude of A cross B is equal to magnitude of A multiplied by the magnitude of B multiplied by sine of 90 degrees. Sine of 90 degrees is 1, so it's just equal to the magnitude of A multiplied by the magnitude of B, which we just saw here. 2 times 2 gives us 4. Okay, the vectors AB and A cross B form a right-handed system, okay? And that should make sense. What that means is all those vectors are mutually perpendicular. So what you've got is a system. Another way you can think about it with your right-hand rule is everything's at right angles to one another. We've got vector A cross B, then we've got vector B, and we've got vector A. So they're all at right angles to one another. Okay. And then we can just start to think about what happens if we take the cross product of our unit vectors. Now remember, we've got our unit vectors I, j, and k, sometimes known as our component vectors. And if we were to take I cross I, we would basically have this situation. So just imagine that these vectors are scaled down a little bit. And these all have a size of 1 now because we're talking about component vectors. But yeah, if they're I cross I think you would agree would be 0 because the component vector in the x direction, which we call I, is parallel to itself. So it's going to give you the 0 vector. Now I just want to make this point really clear. The magnitude is 0, but the result of the cross product is always a vector. So I crossed with I is equal to the 0 vector, not just equal to the 0, the number. It has 0 magnitude and no direction. Similarly, j cross j is going to be equal to 0 for the same reason, and k cross k will be equal to 0. Okay? Similarly, if we keep moving down, I crossed with j will be equal to k. Okay? And so that's the situation we had here. Okay? This should make sense. Just imagine these all have a size of 1. If we cross I with j, we're going to get k. Okay? If we cross j with k, we're going to get I. Let's think about that. Yes, that makes sense, okay? If we cross j is pointing in this direction, so we point our fingers in that direction, and we curl towards k, which is on the z-axis, so we're curling this way, and I is then therefore pointing out this way. Okay, I encourage you to just keep thinking through them. Maybe I'll just talk about one more. J cross I. So now we're pointing our fingers in the direction of j, which is this way, sort of into the page along this green here, and we're crossing with I. So we're crossing this way, so we're going to get negative k. We're going this way, and then we're curling towards I, curling towards the red part, so we're going to get negative k. So that would be this situation. Well, that's the resultant vector. That's the resultant vector in that direction. Hopefully it's making some sense. Yeah, it's an interesting idea. I think once you see this diagram and how it sort of works, it should make it clear. All right, let's keep moving. Okay, so we've spoken about the geometric interpretation of the cross product, which is very important. But what if we just want to sort of just do it using the components? We just want to crunch the numbers and we want to work out the component definition of the cross product. Well, what we're going to do is we're going to invoke this interesting rule. So, sorry, before we get there, let's just talk about this. So this is the component definition of the cross product. If you've got two vectors, A and B, A is A1i plus A2j plus A3k, and B is B1i plus B2j plus B3k, then A cross B is just equal to this. Okay, A2B3 minus A3B2i minus A1B3, you get the idea, you can read that. Okay, but then I suppose the question is, why is that the case? And one thing we're going to invoke is this idea that the cross product is distributive over addition. So what that means is A cross B plus C is equal to A cross B plus A cross C. And let me explain that in a bit more detail. So let's just look at this left-hand side, A cross B plus C. So let's do a bit of a diagram over here. Okay, we've got some vector A, right? There it is. Okay, and we've got some vector B. There it is there. And we've got some vector C. So you can see all our vectors here, A, B, and C. What we want to do now is we want to look at vector B plus C. So B plus C is this one here. So just showing you that again. If we add vector B to vector C, doing some vector addition, we'll get vector B plus C, which is here. And then what we want to do is we want to cross A with B plus C. And you'll notice, if we do that, we know the cross product is perpendicular to the plane containing A and B plus C. So you can see that we get this resultant vector, A cross B plus C, sort of pointing perpendicular to those two vectors. And obviously we point again, we start at A with our fingers in the direction of A, curl towards B plus C, and then we get A cross B plus C pointing in the direction shown. Okay, what we're going to do is I'm going to pause the video. I'm going to show you the other way, show that it works. And so here we go. It's a bit messy, but hopefully you can see that if we take, sort of look at the right hand side here, A cross B plus A cross C. So A cross B, if we cross A and B, we get this red vector, A cross B. And if we cross A and C, we get this blue vector here. And lo and behold, if we add them together, A cross C plus A cross B, then we get this vector here, which was the same vector, hopefully you can recognize, as A cross B plus C. So that's just a demonstration that the cross product is distributive over addition. So that's an important idea, because as we come to prove the cross product now, the component definition of the cross product, we can see that when we cross A and B, we're going to get A1I plus A2J plus A3K crossed with B1I plus B2J plus B3K. Okay, and now using that distributive property, it means that we're going to have to cross A1I with B1I, A1I with B2J, A1I with B3K, and similarly A2J with B1I, A2J with B2J, A2J with B3K, A3K, B1I, A3K, B2J, A3K, B3K. Notice that this is what you get. You get this monster, but it simplifies nicely. So using the properties of the cross product, which we spoke about on the previous slide, you can see here we've got things like I crossed with I, but we know that that's equal to the 0 vector. And there's a slight typo here, these should be bolded zeros, right? But these are equal to the 0 vector. So substituting those values in, this part disappears. Okay? I trust that you can sort of crunch the numbers here. This one here will also disappear. So you end up with this. B1K minus A1B3J minus A2B1K plus A2B3I plus A3B1J minus A3B2I. Collect the relevant terms and take out the components as factors, and then we've proven the component form of the cross product. Takes this form. Okay, so reasonably confusing stuff, I think, but interesting nonetheless. Let's look at the last thing, which is, say you get given two vectors and you need to compute the cross product. How would you do that? Well, let's look. We're going to use what's called finding the determinant of a 3x3 matrix. And I've made another video about this, so I'll put the link down below for that. But basically, if you have to cross two vectors, A and B, you set them up in a matrix like this, and then you find the determinant of that matrix. So you would do the I component multiplied by the determinant of this mini matrix here, minus J multiplied by the determinant of this mini matrix here. And then you do all that, and then you'll get this as your cross product, not the dot product, sorry. Of the two vectors A and B. Let's just check that that matches from before. A2B3 minus A3B2. A1B1, A1B2 minus A2B1. I think it looks pretty good. So that is how you do that. Yeah, hopefully you found that somewhat useful. If you did, even if you just found the slides sort of helpful, please give us a thumbs up. Tell your friends. Let me know if you need any private tutoring, and good luck with all the work that you're doing, and I'll talk to you soon.